good evening, or afternoon as the case may be. Thank you very much for coming in to see our talk. The talk is Designing Systems for Continuous Availability and Scalability. So if this isn't the talk you're supposed to be at, you should leave now. My name is Jim Pinkerton. I'm an architect in the file server team, and we'll be walking through the first half of this talk.
I'm Surendra Verma. I'm a dev manager in the Windows Core group for the storage and file systems area, which is file systems and disk stack and storage spaces and all that stuff. So yeah, Jim's going to start, and then I'm going to come on in later and do the second half.
Yep. So just to briefly walk through what the agenda is for the talk. I'm not sure, people may or may not have been able to attend the prior talks in the day. Thomas Finning walked through the business value around continuous availability. This talk will then dive into more of the technical details of the continuously available platform. So I'll be walking through that, trying to give you somewhat of a more formal definition of what the platform is and how we think of continuous availability. And then from there, walk into a little bit of network fault tolerance and the new capabilities we have in Windows around NIC fault tolerance, as well as new scalability improvements for the file server. And then Surendra will be walking through the new enhancements to NTFS to be able to improve its availability, and then the new cost-effective critical storage solution called Storage Spaces. And if I can. So starting with the basics, what do we mean by continuous availability? There's really kind of a bit of a subtext in terms of what is the goal. To me, the goal is we want to be able to create a continuously available platform using existing industry standard servers. But there's also a sub-goal underneath that. The reality is that you can improve the scalability of today's standard servers by deploying some of these new capabilities that we have enabled in Windows 8 with our partners. Thomas in this morning's talk walked through some of the partner innovation that's been going on. We're very strong believers in it. It improves the scalability substantially, both on the storage side as well as on the networking side. Things can change quite a bit by changing the platform. But let me dive a bit into continuous availability in case you did not see his talk. What we're really thinking of it is in terms of a system. It's not about software, it's not about hardware, it's about the application's perception of what's going on. So what we want to be able to do is look at a service and that all components that the service requires are continuously available so that then they can be enabled to be continuously available. And there's some services that we've made out of the box continuously available. For instance, the file server. For instance, DHCP, several different platform components. So it's this combination of hardware and software that need to work together in tandem. And then when you fail over, for us, we walk through in the morning a single node versus clustering. The reality is you have to maintain these hardware platforms. And so if something breaks or you have Patch Tuesday hit you, you need to be able to move the load in a transparent fashion to a different node. That movement needs to occur without any data loss. It needs to occur without any interruption to the service. You can stall an I/O for a short period of time and they won't complain. But if you stall an I/O for 60 seconds or 90 seconds, often the timeouts will hit you in the application and therefore it will not be transparent. So what is transparent then? Well, transparent simply means that the application doesn't really notice. Typically, we talk about brownout periods and blackout periods. And the really critical thing is the blackout period. If that blackout period means that the service cannot function, then clearly you're not failing over transparently. So moving into a little bit of a definition of what is the platform. As Thomas walked through this morning, we actually start with a single node and try to improve that as much as possible, and then go into multi-node, where we can talk about using clustering technology to create continuous availability, and then potentially go all the way into multi-data center solutions with Hyper-V Replica. For the context today, though, for this talk specifically, we'll be focusing on single data center, and even all the way down to a single node. You can argue a single node, by definition, is not continuously available, because you potentially have to service that hardware or service the OS. In feedback from customers, They can buy the definition, but the reality is they really would like an improvement in availability. A lot of them claim that cables are a real issue. Network infrastructure or storage network infrastructure can be real issues in terms of availability. And so what we've done is created innovations to improve storage availability as well as network availability, even for a single node. So when we talk about a single node in terms of HBA improvements, we'd like to see multiple controllers going off of a single node, so that if a single controller dies, you can use our existing functionality with multipath I/O to be able to fail over, and then potentially enable the new capabilities we have around external JBOD to provide a broader spectrum of storage solutions at lower cost points. On the networking side, what we'd love to see is multiple NICs, and with the new capabilities in Windows 8, we can now fail over between those two NICs. And then we also support RDMA as well, which I'll get into in a little bit, which improves scalability. But of course, for truly continuous availability, we need clustering. We need to be able to move the load around so that we can service individual nodes. So we really want the platform to be at least 2 nodes, and potentially many more than that. As was alluded to in prior presentations, we now support up to 63 nodes in a cluster. And then, of course, the same network infrastructure can be utilized for the cluster interconnect as well. And so going down the RDMA path can potentially much reduce the overhead of storage transfer on the cluster. So with that, then, I wanted to just kind of briefly summarize what are the things that we view as kind of minimum requirements to be continuously available, and then what are really nice to haves that, depending upon what price point you're trying to hit, may or may not fit in the budget. What we're not trying to do is define some Cadillac platform that often commiserates with extremely high cost. What we'd like to be able to do is define, or what we're doing is defining the simplest system, which to me would be a single node that has essentially no fault tolerance. And you add nodes in so that if that single node or any component on that single node fails, you can fail over to another node. And so if you note, what I've done here then is if we go down the single node path, I've already kind of walked through the different things we want. The main issue is we need reliable storage. We need redundant storage because disks particularly fail, and if they fail, you lose data. That's not acceptable. And then from there, it's really about scale and potentially have better SLAs, service level agreements, because you can now scale and be fault tolerant as a network interface fails or a storage interface fails. And then potentially, again, if price point allows it, have hot swap components, hot swap PCI bus, et cetera, for that single node. Then when you go into the multi-node, the same arguments still apply, but for us to be able to fail over transparently, we require shared storage. And so that shared storage that is reliable on a single node needs to now be reliable as you share it across multiple nodes to support the transparent failover. And so with that, this is my introduction of what we've had to do to be able to pull off continuous availability specifically for storage. As you can see, I've also mixed in networking because for the file server and for iSCSI specifically, networking does come involved. This is a heck of an eye chart. I'll let you read it at your own leisure. I won't be going through it here. But what I wanted to do was give a little bit of context as to how much cross-group collaboration we've had to pull off continuous availability. It is not about one single group fixing a bunch of bugs in their problem, in their feature set. It's all about tying it all together end to end. And so we had an amazing cross-group collaboration, going all the way from the storage stack and our partners there, up into the file system, through to data management, the clustering infrastructure, the clustered shared volumes version 2, the file server team, the networking team, the networking devices team, and Hyper-V, as well as all the management infrastructure. We've all had to work together very closely within Windows and also with our partners to be able to pull this off. So clearly, this is way too much for one talk. We actually created several talks, 7 to be specific. This is the 3rd talk in the series, Designing Systems for Continuous Availability and Scalability. And then the talk after this will be going through multi-node with block storage. So that's going through clustering when you have block storage, shared block storage. And then the 444 session is around remote file storage. And then tomorrow morning, in this same room, the Hyper-V team will be walking through the features that they've created to enable continuous availability in a virtualized environment. And then we'll conclude with a talk walking through creating NAS appliances that are continuously available. So that's the series. So I'm going to focus now on single node specifically, and then we'll kind of start winding through that in terms of first the device program that we've enabled for storage and for networking, and then some of the capabilities that lay on top of that light those new device capabilities up. And then from there, we'll go into a bit more of a deep dive on the platform storage. So starting from the left then, in terms of new hardware capabilities that we light up with Windows 8, we have a new way to virtualize storage and make it reliable called storage spaces that Surinder will be walking through very shortly. We also have a new device program for shared JBOD to be able to have just disks in an enclosure that are managed natively by the platform, and what hardware requirements we have for that to make sure we can do things like light up the LEDs when a disk fails, things like that. We've created a new device program for clustered RAID controllers. It's a new capability to enable in a clustered environment to deploy a RAID HBA. And the problem classically with the RAID HBA is that if you have a write-back cache and you fail over, all the dirty data in the write-back cache is gone. You just lost data. By definition, that's not transparent failover. So we had to work with our partners to define this new class that effectively enables them to mirror the cache so that a single node dying doesn't mean you lose data. And then finally, we've also done a lot of work for external storage arrays to enable new offloaded capabilities, be able to enable trim, and also to be able to do thin provisioning and thin provisioning notifications. And then as you build that out to the right, then I'm going to skip over the Windows components and focus on devices. On the network devices side of things, we have new Fabric support. In Windows 8, we will be supporting InfiniBand as a core device with an inbox program for it. For new network device capabilities, there's several new offloads. I'm not even going to try to go into them right now. I would recommend you look at talks 433 and 437. They walk through them in much greater depth. But the bottom line is those capabilities are used for the cluster interconnect and then also for the file server. So if you choose to deploy instead of a single cluster with your compute and storage co-located together, if instead what you choose to do is have compute being able to scale out separately from your storage, then you can use the file server to be able to do that using file-based storage instead of block-based storage. We'll be walking through that in the 2 talks from now. So let me then dive in a little bit. This is going to be a whirlwind summary of some of the new capabilities that directly apply to fault tolerance. There is another talk on NIC teaming, talk number 433. I just mentioned it briefly here to make sure people are aware of this new capability. It's very easy to deploy. It's fully integrated with Windows. NIC teaming is not a new technology. It's new to Windows. Many different OEMs and IHVs have been shipping NIC teaming. NIC teaming enables you to put together several NICs into a single virtual NIC. And that NIC teaming capability, that IMMux shown here, will then load balance across them. You can deploy it as an active-active or active-passive. So active-active would load balance across, and then if any single NIC fails, it would fail over to another NIC. It does this by link-to-link failure detection. So you can deploy this with cooperating switches, and they'll do link-by-link detection and then fail over in case any link dies. So this is great technology, but to me the really new thing is we now support it. Previously, if a customer called and said, I've got some third-party teaming solution, the first thing our customer support would say was, turn it off, and then I'll help you debug. Now people can deploy this and feel confident with it. The big caveat with this technology is that the way it does load balancing across the teams is it will take a single TCP stream and put it down a single NIC. This is required because TCP requires things to be in order to be able to go fast. And of course, that's the goal here. And so when you look at this technology combined with technologies like receive-side scaling, which we shipped in a previous version of our OS, effectively what that means is if you have a single TCP connection, you will be able to saturate one core, but you won't be able to saturate more than one core. As we all know, the cores are not getting faster. What we're getting is more of them. And so that was a core problem that we felt we had to solve for SMB specifically. This is the file access protocol, the new version of the file access protocol. Because for storage traffic, we wanted to be able to hit the highest levels of performance and not be bottlenecked by a single core. So to solve that, what we did was we made a full-blown SMB22 session, and then underneath that enable multiple TCP connections. This is useful in a variety of deployments. It's actually useful just for a single NIC. A single NIC, say a 10 gigabit NIC, can actually pretty easily saturate a single core. If you go with small IOs, you can saturate a whole bunch of cores if you can scale out to multiple cores. And so that, even for single NIC deployments, if they advertise receive-side scaling, will then open up multiple connections automatically. There's no configuration required. When you then go to multiple NICs, you can deploy it with teaming. So teaming allows you to deploy a single IP address. Or you can also deploy it without NIC teaming. And in that case, you have to deploy an individual IP address for each NIC. In either case, we will support failover. Failover for the SMB case, we actually use end-to-end checks. So we don't do link by link. So it actually fits very nicely with the link by link checks that you get with NIC teaming, combined with multi-channel to do end-to-end checks. So if there's anything else that has gone wrong on the link end-to-end, we'll then fail over to another path. And then, of course, the throughput can be pretty fun. This is an example. This is all very preliminary data. This is very early still, pre-beta software. But the bits that you got at this conference will do this. If you plug 4 10 gigabit Ethernets into a system, going between two systems, you of course have to have a storage subsystem that can do 4,300 megabytes per second. This was all of 18 SSDs is all it took to get these numbers. The full data, we're publishing a white paper tomorrow on our multi-channel performance, and you'll be able to get it at this link on the slide. Of course, to be able to hit this kind of performance, you have to have the ability to span out across multiple NICs, and so it's critical that we have receive-side scaling support. And then as you can see, we're getting near linear improvement as we scale the number of interfaces if we're above the 32K or 64K range. And you can see we fall down pretty quick when we get into the smaller I/O sizes. If I had charted the CPU utilization, which the white paper does chart, you'd find that change is right when all of the cores start getting saturated. So the good news is we scale amazingly well. The bad news is that for small IOs, we still have a CPU bottleneck, which I'll hopefully solve, which I'll show you how we solve. So in summary, in terms of the network traffic, all of the offloads that have been shipped for network interface cards in prior releases are being used, as well as the new receive-side coalescing to get the prior slides' performance numbers. And so all of those are great to deploy in terms of continuous availability and scalability, as well as potentially the virtualization work that's been going on, the GRE and dynamic VMQ. I would highly recommend you go check out Talk 437 to learn about those capabilities. But we still have this issue around CPU utilization. For large IOs, we can get full throughput, but the application would really like to have that CPU to do some work. If you're running SQL on top of the file server, it has, and SQL is doing OLTP transactions of 8K IOs on average, we've got a problem. For large IOs, we scream. But again, the CPU utilization is high. And this is why we invested in RDMA. So RDMA, I'm providing a summary overview here. RDMA is really just a DMA engine, a direct memory access engine, that goes between two computers over a network. And it does it in a secure fashion. It's been around actually for a while, as has been mentioned in other talks. It was primarily an HPC technology. And so really the new thing is we're now putting it in Windows as a core capability for the data center. What it provides us is two really fairly key scenarios for us. For the file server with SMB22, if we've got an RNIC, we call it an RDMA NIC, in the system, we will automatically detect the RNIC and automatically transition to RDMA mode instead of normal TCP/IP mode. And that can radically reduce the CPU utilization. I'll show you some numbers in a second. And it can also leverage the multi-channel work. So if you look at some of the performance capabilities we get out of it, this is, again, still very early. This is, again, pre-beta software. But with a single interface is about 32 gigabits per second, but it's currently limited by the speed of the PCIe Gen 2 hardware, which is soon changing, right? The PCIe Gen 3 hardware is in alpha as we speak. The bandwidth we achieve is roughly 3,100 megabytes per second from a single client to a single server, and scaling nicely as we add clients. If you look at the CPU utilization, so first off, the performance of a single interface is pretty spectacular, going over InfiniBand. The other side, though, is when you look at the amount of CPU being utilized. So for the client side, which is honestly the important thing, that's where, for instance, SQL would be running or Hyper-V would be running, we've gone from saturating all the cores with 4,200, with the 10 gigabit multi-channel work previously, we're now using roughly 80% of one core on a 4-core machine on the client. And on the server, server has to be a little bigger because we had a lot of PCIe slots in it. It had 12 cores, and there we're only using 140% of one core. So it's really pretty substantially different. What we've there is a lot of difference between the different RDMA NICs. There's actually 3 standards that have been created for RDMA. We do support all 3. First, on Ethernet, we have 2 specifications. We have the one that's been done by the IETF called iWarp, which sits on top of TCP/IP, so it's routable. It works over all existing switch infrastructure with no changes. Then we have RoCE, which was defined by the InfiniBand Trade Association. RoCE stands for RDMA over Converged Ethernet. It's also very high performance. It does require DCB switches, so you have to be able to configure and deploy the DCB switches to be able to get RoCE out there. And then for InfiniBand, we also support it as well. It's much higher link speeds. Today, you can get 32 gigabit, and very shortly, as Thomas showed in his talk this morning, he had a card that was the 56 gigabit FDR for InfiniBand. So you can get some pretty amazing performance out of it. And again, Talk 433 will go through that in much better depth. And so with that, I'd like to hand off the mic to Surendra. He'll then walk through the storage improvements in Windows 8. You need this?
Oh, yeah, of course. Yeah. Thank you, Jim. So I'm going to use the rest of the time and talk about improvements in storage in Windows. And just to tie in with what Jim's been talking about, continuous availability and scalability, it's really important to realize that in order for the systems to be continuously available, the file system has to have very high integrity. It needs to be able to handle situations where a system crashes or a power loss happens, We don't want the file system to get corrupted in those cases, of course. And we also want to make sure that if it does get corrupted, we don't want it to be offline for too long, because when it is offline for too long, that's your data. Your system is not available if your data is not available. And since we are relying a lot on shared storage, it's even more important that the place where everything meets, which is the file system at the end, is really, really good in these respects. So I'm going to walk through a few things we've done in this topic. All right. So the first thing here is to make NTFS much more reliable on industry standard storage, or I would just call it SATA. We've historically had some issues with SATA where force unit access has not been consistently supported, and NTFS algorithms rely on that to be consistently supported. And we've had cases where on crash, the volumes end up being corrupt as a result. What we have done in the next version of Windows is changed NTFS so that at strategic points in time where it's extremely important for NTFS to maintain write order, it issues a disk cache flush. What this does is that it maintains the write order that's necessary to keep things consistent on the disk, while at the same time, it allows the disk to cache data for as long as it can and reorder writes within that interval if needed. And we found that this, in our crash testing that we have performed in our labs, we have found this to have improved our reliability numbers by a very, very significant amount, like multiple times. So I think this is a really, really good improvement. It should help everyone, even people running on laptops, all the way up to people running these servers, the kind of servers we've been talking about. The next thing I'm going to talk about in a little more detail, this was also mentioned in the talk by Rajiv, for those of you who attended it, the previous talk in the series. So we now have taken this check disk utility, which in Windows 7 would take the volume offline for as long as necessary to scan and fix the volume. We've essentially broken it into two parts. The first part is the checking phase, and the second part is the fixing phase. And in doing so, what we have done is that the checking phase, which is really the time-consuming part, we've changed the system so that it can actually run in the background. And in that scan mode, which is the background scan mode, which is online, it identifies corruptions, the precise corruptions that exist. It logs those precise corruptions, pinpoint corruptions. And then in the second phase, we take the volume offline for a really short period of time to go fix just those corruptions that we have already logged and we understand. We've also enhanced NTFS so that some corruptions are fixed without taking the volume offline at all. They will be fixed during the scan phase. We had that support in Win 7 as well, with online fixing within NTFS, and we have extended that to more cases. We also went through a lot of analysis of telemetry data and really understood the cases where check disk is offline for the volume is offline for a long time, and really went and focused on those long-running cases. So we hope to see a huge amount of improvement in this area. Just to go into a little bit more detail in this, here is the state flow. And so as you can see at the very top left, NTFS will detect corruption when a file is accessed and a structure is found to be corrupt. It will flag the corruption to be verified. Oftentimes, NTFS will find transient errors which actually do not result in on-disk corruption. So those things are eliminated upfront. They don't need to be fixed. For those that are truly on-disk corruptions, those are flagged to be scanned in this background mode. And some of those will get healed online, as I mentioned. And those that cannot be will be logged. And then we have the spot fix phase. So there are these phases called scan phase and the spot fix phase. The scan phase is the online scan, and the spot fix phase is the one that's offline, which is much, much shorter. And here is an illustrative example of the difference in the time it takes, difference in the time for which the volume is offline. The red bars indicate the previous version of Windows to handle just one corruption. This is in a 100, 200, 300 million file case. The difference comes in the fact that in the previous version of Windows, we would take the volume offline to check the entire volume to find out what was corrupt. Now, the phase where we actually have to spot fix the specific corruption is down to the point where I can't even mention it. I mean, you can't even see that in the graph. It's really, really small. It's less than 8 seconds in this case, compared to 350 minutes in 300 million files case in the previous version of Windows. So there's a huge improvement here, and this directly translates to the availability of the file system, which translates to the availability of the entire system and the multiple systems that are running on top of that storage. So we think this is going to make a really big impact. So let's go through a demo here to show you the various phases of check disk. And this is an illustrative demo, and it's going to be a really small volume. So it will not show you the time difference, but it will show you what really happens in these different phases. So I am going to be running this through PowerShell. And here we go. So instead of typing all these here, I have a mechanism to have these pre-typed scripts come up. But I will explain what's going on here. So I'm going to run the script. And the first step here is that I'm going to look at the volume and see its current status, which is shown to be healthy. And if you notice this is a new PowerShell command. This is one of the series of new PowerShell commands we've added to manage volumes and in this respect. So I'm going to go corrupt this volume through this utility that we have. And what I will do here is I will show you the volume, which is here f:. Let's take a look at it. It has the entire Windows directory, so it has a bunch of files. And then we added another file here, and we corrupted it. That's what I just did. And as you can see, when I tried to access it, we got this error, which is familiar to all of us. Now, at this point, NTFS is going and doing a verification to see if the file is really corrupt. So there's a little bit of we've injected a sleep here to ensure that that process happens. When that completes, you can see that the volume has transitioned to a different state called scan needed. So there's a verified corruption. It needs to be scanned. Ordinarily, this will happen automatically. This will happen at the next time Windows finds a good time, okay, within a few days or within up to a week. And then it will happen in the background. Now, but you could do this manually, and that's exactly what I'm going to show you. So I'm going to run scan on this. And this is a new flag. We have new option we've added to check disk. And as you can see here, the check disk output shows that it found some corruptions. And the important thing is it said it queued for offline repair. So it actually did not repair it because it was running online. The volume was actually up here. You can see that it was the window is still around. Explorer window would have died if the volume had gone off. So it all happened online. And this would have been the time-consuming phase of check disk. Now, the next state that we got into is spot fix needed. We verified it. We know exactly what needs to get fixed. It's logged on the disk. And if the system were to go down and come back, we remember that because it's actually logged on the disk, on the volume. So the NTFS will know that. And so let's go ahead and do a spot fix. This is the part that you would have to do online. And as you can see, this took almost no time. It was almost instantaneous. Of course, the volume went offline during this interval. So here you can see how the various stages of check disk work. And just to show you, let me get this window here to show something here. So what we did was we captured a screenshot for how long this would take for a much larger volume. And we ran check disk on it. This is a Win7 output. And so here it says that it started at 4:37 p.m. It ended at 4:50 p.m. So it took 13 minutes. Okay, I think this has 10 or 20 million files. And the same volume, I have it here. And I have already run the scan on it, which was the online phase. And I will show you, if I were to spot fix it, how long that would take. So this actually will show you the availability improvements that we've made. So this is really, this shows the performance. So in 0.3 seconds, we were able to fix that, which previously took 13 minutes. All right, so that really shows you what the improvement is in check disk. All right, thanks. So I think you'll find it very useful. We are really happy about this feature. I'm sure you'll like it too. So moving on. So let's move to another topic, which is storage spaces, which is a new cost-effective way for you to manage, for Windows to manage storage for you. This has been covered in Satya's talk and in other talks as well, and I'm going to go in much more detail over here. And I have a few demos to show as well. So storage spaces, for those of you who were not present in the previous talk by Rajiv, I'll take a couple minutes and go through this introduction. It's a powerful new platform abstraction. What it allows you to do is to take disks, typically JBODs, attach them to Windows over SAS or SATA, and you can create pools out of those disks. And then pools, which means you can aggregate those drives within those pools. You can administer those pools. You can create virtual disks over it. So effectively, you're virtualizing storage. And those virtual disks have various resiliency options and various provisioning options. So we actually have just-in-time allocation or thin provisioning or over-provisioning options available for you. And you can just go off, and like here, this is a canonical diagram. It's not an exact diagram, but it shows you that you can have a single machine connected directly via SATA or SAS to your set of disks, or you can take a set of disks and connect them to a number of machines. In that case, the pool is actually shared across all those machines. You, of course, need shared connectivity, and shared SAS is our recommended option there. So I'm going to do another demo here, and I'm going to show you the ease of provisioning. So what I have here is a Blade server from Dell, which has a bunch of drives, as you can see here. And this is the disk management view of it. So these drives are currently unallocated. So I'm going to go ahead and use PowerShell again. PowerShell is a common theme here, you'll see. And you've seen PowerShell kind of used across all various talks in this build conference. PowerShell is really big this time around. And spaces are support PowerShells very well as well. All right. So I'm going to use the same technique I had previously. I'm going to show you those scripts. So the first one here is a new command which we've added in PowerShell, which is to create a new storage pool. And the input to the storage pool is, so one of the inputs is the subsystem, which is the storage spaces subsystem. In this command, since on this machine, the only subsystem that's installed is the storage spaces subsystem, we didn't have to filter anymore. We could just issue that get storage subsystem command. If there were other subsystems attached on this machine, you would have to then filter it and specify exactly which subsystem you wanted. We give a friendly name of demo pool, and we say that the pool must consist of all the physical disks that are returned by this command, which gets you all the physical disks, which is piped into this where command, which filters that output from get physical disk by all the disks that have not been pooled already. So this is all the disks that exist that have not been pooled at all. Take them all, put them into one pool. It's a very simple command. So let's execute that. And you can see here that those disks disappeared from the disk management view because they have been absorbed into storage space, and they're not available to the system in any other way because pool now owns them. The next step would be to create a virtual disk, which is another name for spaces. So I'm going to create a space here. Its friendly name will be a thin volume disk. It will be created out of the pool that we just created. And there's only one pool, so I'm just going to say get storage pool. I don't need to specify a name or filter the output of the command. And then I'm going to, the storage attribute is mirror, so it'll be a mirrored pool. And the provisioning scheme is sparse, which is thinly provisioned. And the capacity of that is 10 terabytes, which I can do even if I don't have 10 terabytes because it's thinly provisioned, right? So let's go ahead and do that. So I got it. And I just have to do a few quick steps, which is initializing the disk. Let's just move this here so you can see how this transitions. All right. I'll create a new partition on it. And I'm going to format it. It's that simple. So And what is going on underneath is that the space shows itself as a disk to this Windows system, just like any other disk. And because it's a disk, it gets consumed by all the tools, utilities, and everything else that currently work on disk really well. So the compatibility with third-party backup software and everything else is extremely good as a result of that. So it'll just take a second as we go format it. It's thinly provisioned. As we are formatting it, we're laying down NTFS structures, and the space is getting allocated on demand as that happens in chunks around that. And as that completed, and it is healthy, and we have also assigned a drive letter to it, which is O:. So you can see it here. I can explore it directly from here, and you can see it. It shows up in Explorer. It's that simple. It's empty right now. So that's basically what it takes. This is very easily scriptable, very easily configurable, remotable as well. This PowerShell, it sits on top of WMI. So you can see it's actually very, very easy. It's just another software construct in Windows. So let me go off, and let's take a deeper dive into the capabilities of storage spaces. There is going to be a lot more detail on each one of these points, so I'll just go very briefly over them. So we support thin provisioning. There's different resiliency options. Applications can get involved in error correction, which is something unique that we'll go into. We integrate with clustering to support high availability. Rajiv showed a demo of moving VMs around in a cluster. We'll go into a little more detail. Operational simplicity, you've seen some of the scripting, and we'll go into some more there. And then there is support for heterogeneous media within a same pool. So let's start with space utilization and flexibility. So in this picture, you see that in the bottom, there is 40 terabytes of physical storage. And the scenario here that we've shown here is like a hosting scenario. And on top of that, there are two pools, probably created because of isolation requirements and other management requirements. And we'll go into management to explain why that becomes more useful. Within those pools, you can see that even though we have 40 terabytes of physical storage carved out into two pools, 20 terabytes each, we have spaces that are 64 terabytes. Okay? Those are thinly provisioned. And what's going to happen is that you're going to start out. Very little space is going to be consumed in the beginning. It's just what NTFS needs in the beginning of the volume, typically at the end of the volume, and a little bit of space around that in our allocation chunks. And that's pretty much it. And as you start using those spaces, which show up as disks and then eventually get mapped to drive letters as I showed earlier, as they get consumed, they simply get space from the pool as needed. So the space that needs the space that needs most capacity gets the most amount of storage from the pool, and that keeps going. If the pool gets to the point where it's getting close to getting full, then there's a notification that comes out, which this is a bunch of work we have done on thin provision notifications, which also works with external arrays because of really good integration with our partners. The same notifications work in this case as well. The administrator gets notified, and they can then go and add more disks to that pool. And the space that requires that storage will go ahead and consume it. So you can just continue working. So the capacity expansion is elastic. All you have to do is simply add drives to pools, and you just keep going. All right? Another important aspect of this is trim. For those of you who don't know trim, the very easy way to explain that is that it's a command that goes all the way down to the hardware. And in this case, it also goes to the storage spaces, which gives the space back to the pool. So this is the case where you might end up deleting a bunch of files, and you don't need that space anymore. So you can just go off and say, I don't need that space on that volume, which is an NTFS volume, which is logically contiguously allocated. But in the middle parts of it, you can just poke holes. And you can just send, inform spaces about those holes by using the trim command. And space will just grab that space, return it back to the pool, so someone else can consume it. In Windows, in the next version of Windows, we've also enhanced our defrag to really become what we call a storage optimizer. So it, in fact, looks for opportunities and moves things around strategically in order to create these holes so that you can actually get full benefits of thin provisioning and sharing of space across these spaces. Of course, resiliency has to be a key attribute of this. It's an extremely key attribute of availability. Disks fail, bad blocks develop, all kinds of stuff goes wrong. And of course, we have to keep running when that happens. And we have two options, mirroring and parity. Mirroring allows the data to be copied either 2 times or 3 times. It's your choice. 2-way copies or 3-way copies. And in that option, we will, in fact, go and utilize all of the available independent spindles to maximize performance and resiliency. And in the case of parity spaces, we will, again, do the same thing. Parity spaces is single parity. And it is journaling integrated with this. So there's actually a journal. The journal provides reliability in case of system crash. It also improves performance in case of sequential writes. So we can skip a whole bunch of parity related overheads that happen otherwise. So those two options exist, and they are specified per space, and you can have different spaces with different options, all within the same pool, flexibly allocating space out of that pool. And all those spaces are spread across all the disks, or as many disks as we think is necessary to give you the best performance and resiliency. We also have the notion of hot spare. So you can have hot spare on a pool. And the simple idea of hot spare is that, let's say if a disk dies, as in the cross here, a hot spare kicks in. The hot spare was always there. It was part of the storage. We just automatically add it. You don't have to do anything about it. We detect the problem. We enable the hot spare. We just add it to the pool. It becomes like any other pool drive. And life just keeps going. Of course, you never missed a beat, right, because of redundancy. But the importance of hot spare is that we can start rebuilding really quickly. So you don't have to just quit doing what you were doing and suddenly come in and deal with it. You have a little bit of time. And you can see that the data that was on that disk now gets redistributed over all the remaining drives, including the hot spare drive, making rebuild times fast. And at a later point in time, the administrator can come in, take out the drive that's failed, put a new drive back in, and has the option to mark it a hot spare for a future problem. And life just continues. So we think this will really help. The third point here that's important is application-driven intelligent error correction. It's a mouthful, but what it really means is that what we have at the spaces level is redundancy. So we have multiple copies. But spaces really don't know which copies are good or which copies are bad, right? It has no way to know what's a good copy. That is really known to the application. Sometimes it's known to the file system. Sometimes it's known to an application like SQL Server or some other application running up there. They could maintain checksums. They can examine the blocks and decide what is good and what is not good. So what we have done is that we have plumbed a bunch of APIs all the way from spaces, which is at the disk level, through the stack, through the file system, and up into the user mode. And we have given control to the application to be able to do intelligent error correction if they so choose. So before we explain that more, I'd like to do another demo. And this demo will illustrate the resiliency property. Now let's remember that we created this thin volume just a second ago. Let's use it. I have a video here that I'm going to just copy into it. And then I'm going to play it. And then we'll do something fun with it. So that's our new copy dialog. That's pretty interesting. Let's go to that volume, select the video, and play it. All right. Now, I don't have audio, but I think you can trust me that this video is actually playing from there even without audio. You can actually see the picture, right? So while this plays, let me just go ahead, be a little mean to this device I have here. And I'm going to just go ahead and yank out a drive. So this space is created out of these drives. I just yanked it out. Video just continues to play. It's really no magic, right? I mean, it's mirrored. It should work. But the fact is that it actually works right now. I mean, that's really the key thing. For me, it's a scary thing to do. I'm doing it easily in front of you, but it's a scary thing. I know what's going on under the covers. There's a lot of stuff that moves. The video continues to work. We are in a different state right now, so which will show you the health state of the pool. Let's look at it. So we detected that the health state is not quite good. There's a warning here. And you can actually get more information about what's wrong. Let me just go ahead and put that back in. And when I do that, a whole bunch of stuff happens. We recognize that this disk belonged to the space earlier. It knows that it has come back. We look at it. And then we do the minimum amount of work needed to add it as quickly as possible back to the pool. For the blocks that are unchanged, we have to do nothing. For the blocks that might have diverged, we go back and resilver them so that you continue to work. So it takes a little bit of time for all that to happen. Let's see if it actually completed. Well, in this case, it did, because we weren't doing a large number of writes, probably no writes at this point. So we were able to detect that nothing had actually changed. And the pool is actually healthy again. And we are back to normal, and we keep going. Now, intermittent faults can happen, and disks can sometimes get disconnected and reconnected. Those kinds of things get handled very seamlessly, as I've shown you here. Of course, as I said earlier, if the disk had completely died, the system would have continued working. You could have then had the option to get a new disk and insert it, and we would have resilvered as needed. So that's the demo about resiliency, which shows the obvious thing, but the point is that it actually is working right now, and we're really happy about it. Thank you. So moving on, I had mentioned intelligent error correction. So I'm going to geek out a little bit and show you a little bit of code, since this is the build conference. And I'm not going to type it here. It's pointless. I can summarize this in a way that you don't have to read everything. It's very simple. We have an API called read file. Everybody knows it. It's the same API that you can use to read files. We have modified it. So what you do is you open a handle. You change the property of the handle to specify which copy you want to read. So if you have 2 copies, you can specify 0 or 1. If you have 3, 0, 1, or 2. And then you can just call read file, just like usual. And that command, that API is plumbed all the way down to spaces, and spaces will give you the specific copy that you want to read. Now, if you wanted to write your own scrubber, you could write it. You could scrub all your data, read all the copies, make sure they're all good. Another scenario for this is that you just did a normal read, and you did some verification. You found that there were some problems in the data. Then you can call this API and say, let me see if the other copies are good. OK? So now, if they are good, we have another API, the device I/O control, which goes all the way down to spaces and asks spaces to use one of the good copies to repair the bad copies. And all the parameter setting here is effectively doing that. It's basically saying the good copy is copy number this, and the bad copy or copies are copies number so and so. And then you call that API, and spaces will basically use the good copies and fix the bad copies. And that's it, and you keep going. And we think this will be tremendously useful, because if you look at some of our enterprise applications like SQL Server and Exchange, they have inbuilt checksums. They have checksums on their pages, and they handle a wide variety of faults. And this is one of the big reasons for them for their downtime. And they've built a lot of features around keeping the system going, containing the fault, and those kinds of things. We think that by using this plumbed all the way down to spaces, they can really, really improve their experience. So moving on, I had mentioned this earlier, the reasons for creating multiple pools. But let's popping up. There is a lot of operational simplicity that happens because spaces are just another Windows component. It's managed just like any other Windows component. So the management happens via the new Windows Storage Management API. Rajiv talked about that in the previous talk. That API is not limited to spaces. It actually manages a wide variety of storage in the box and external arrays. It's the same API. The same API is effectively plumbed down to spaces. Now, because these are Windows objects, the management of spaces is very flexible and very granular. For example, you can actually assign ACLs to some of these objects. And then you can go off and say, OK, I'm going to delegate management of this pool to that authority, or that pool to that authority. So in the cases where you have multi-tenant deployments, like hosting, for example, you can imagine how valuable this would be. And there are a whole bunch of other administrative controls that are very granular that I won't go into in detail, but you're welcome to look at and more details later as we publish them, where there are commands to set properties of spaces, properties of pools, redundancy levels, all kinds of things. Of course, I had also mentioned this. Of course, because it's PowerShell and WMI, it's remotable and scriptable. That should be obvious too. This picture basically shows that you can basically map your service level agreement, the quality of service you want in your workload, map it down to the specific hardware capabilities. So within the same pool, you can have some SSDs, you can have some cheaper nearline storage or more expensive somewhere in between HDDs. And within the same pool, which is within the same unit of administrative control, you can actually deploy your applications and map them by mapping spaces to those media. For example, you could take finance and put it on your solid-state drives, or you could deploy SQL Server, where your database, your temp DB goes to certain kind of storage, your main database goes to some other storage, and log goes to some other storage altogether, right? And you have that level of control. So here's a picture that hopefully summarizes a lot of the concepts we've been trying to get across. And it's a little bit of an eye chart, but we should spend some time looking at it. So there's effectively essentially two parts to this picture. There's a physical view and a logical view, one above another. So let's start with the physical view. What we have there, again, it's a canonical picture. It shows a series of deployable elements on a network. What I mean by deployable element is basically a set of compute elements attached to a set of storage. All of the storage is visible to all of those compute elements within the deployable element, as we call it. So in this case, there's 4 blades and a whole number of disks in a JBOD configuration. As we mentioned earlier, we can cluster spaces, a pool across machines, right? Across nodes, in which case these blades. So we can create, in this case, what we have done is we have created a pool, just for simplicity, one pool for every deployable element. You could have created more pools if you liked. And that pool is clustered, and it has 64 terabyte spaces, multiple of those. And then above that, we have CSV, which layers directly above that and provides a distributed, uniform and distributed namespace across all of those elements underneath. So you can see them all and manage them all from one place. They're all volumes that can be managed. Above that are workloads, and you can see that there is a little bit of affinitization going on bottom to top, which sort of makes sense for performance reasons. But I should point out that CSV has been, as Jim mentioned, CSV has been updated to take advantage of the RDMA support that's been done. So it is possible to go asymmetric, and for it to, in fact, service in occasional cases requests when things are not perfectly aligned. And RDMA is pretty good, as we have seen. So what this shows you is that you can start with these deployable elements and scale them out sideways, and then have resiliency within storage, very easy failover across machines for failover reasons or for management reasons, for load balancing reasons. And then above that, you got a very nice namespace for management. And above that, we have your applications running, your workloads, and they're very seamlessly managed. So hopefully it gives you a little bit of a broader picture of what's possible with what we are doing. And Jim kind of referred to some of these broad work that we are doing in the talk in the slide he talked about, the big slide. It relates to that. So in summary, what we have communicated is that in this version of Windows, we have made very, very big improvements, starting at the very core of our storage stack, which is the file system, building new abstractions for storage for resiliency, and a whole bunch of work we have done around network scale out and resiliency. And this we believe will create a really, really nice opportunity for a lot of our partners and our customers to go off and to build and deploy scalable and reliable solutions. And Jim, do you want to add something to that?
Yeah, hopefully we've started with a bit of a foundation in this talk to help you understand what is the continuously available platform and how it scales. The next talk after this, if you could go to the next slide.
Yeah.
The next talk after this will be going through the multi-node with block storage. That is foundational for the next talk after that, the file server talk. They actually build cleanly on top of each other. And then the Hyper-V talk tomorrow morning will then take all of the work of those two talks, 450 and 444, and then show how Hyper-V layers its continuous availability features on top of that. So I would encourage you to see those talks as well. If I get you to go back one slide.
Yep.
And please send mail to either of those if you have any further questions around either storage platform or around continuous availability. With that, any questions? Yes?
When does the trim operation run? What triggers the trim?
Okay. So the question was, what triggers the trim operation? When does it run? The most common reason for running trim is when NTFS frees space. When you delete a file and some space is freed up, shortly after that, when we know we don't need to use that space for recovery, there's a little bit of technicality there, but once we get past that window, we send a trim down. And that will happen as long as the trim is sent down the stack, then it goes to the device if the device supports trim. So even on laptops running SSDs, this actually started in Win 7, where SSDs needed free space, and it was sent down to SSDs. The same thing applies on servers as well. The trim command is a SCSI command. It goes to the device. And one other time when it will run will be when the storage optimizer will, in the background, look for opportunities. And it will, as it runs quote-unquote defrag, it will keep contiguity of free space in mind and then send trims down. So those are the times when we run it, and then I suspect we run it on format as well. Yeah.
Other questions? We're actually about out of time. Sorry, one last question?
Have you seen any information or any configuration about the topology of the distribution of the disk? Because Stripe, there is mirroring, the right configuration is 110 or what? So you can set that.
Oh yeah. Okay. So the question is, what are the configurations for striping and mirroring and things like that? Okay. So yeah, we actually did not go into details of that. However, I can explain this at a very high level. Space is thinly provisioned. It is allocated in relatively large chunks. The chunks are we are during development, and we have a size that we are tuning right now. Imagine order of hundreds of megabytes, roughly that. So we just allocate in those chunks, and then we'll stripe as we can, and then we'll ensure that multiple copies are kept on multiple spindles for recoverability, and we just have an optimal algorithm that just goes out and does that. And we also take into account your administrative calls preferences, such as the space must belong to a certain drives. So we take that into account as well.
So you can stripe.
You could draw an analogy with Azure at a very high level, 50,000 foot level. Right. There's exactly. There's failure domains, and we ensure that the storage is always across failure domains when redundancy is required. We do striping when necessary for performance. You could say that. Yep.
All right. I think we're a bit over time. Anybody else has questions, please come on up, and we'd be happy to chat with you.
Yeah. Thank you very much for coming, and we'll be around here to answer questions. All right.